Now, one of the things that we came up with the introductory video on gravitation is that the gravitational force, the force due to gravity, is proportional to the product of the masses, and there was a gravitational constant g, and we had the masses, let us say m1 and m2 are the masses, and they are separated by a distance, so it is proportional, inversely proportional to the square of the distance, and the direction obviously is uh, related to uh, to which body is attracting the other. Now, that's more or less the framework of it. But what we also learned is that from this value, that the from this phenomenon, that force here is inversely proportional to the square of the distance that is separating the two masses. That means as the distance increases, the force or the gravitational pull, of course this is the only force which is attractive in nature. There are other forces which are attractive as well as repulsive, be it in case of electrostatics or the magnetic forces. Most of them, in fact both of them, are attractive and repulsive as well, but this is one of the forces which has the attractive characteristics, no repulsive characteristics yet. And so the force always tends to attract, due to the force a body tends to attract the other. Now let us take the case of a mass here, let us say capital M, and it is attracting every object of a certain mass towards itself. It has certain force acting on it, depends inversely on the square of the distance. So as the distance increases, if this mass is obviously uh, taken away, then it goes, or it moves away from the gravitational pull, or we can say that the gravitational force goes on decreasing, and it also decreases exponentially with the distance, exponentially as the square of the distance. Now, the result that we can come up with is something like this. Graphically, we have this value to be somewhat like this. Now, if the distance is zero, let's take the distance in the independent axis and the force is on the dependent axis. Now the distance over here, as it is zero, the force, obviously with the distance zero, anything divided by zero is undefined, so the force is infinity. It'll meet somewhere in the force axis, but it'll meet at infinity. So this is asymptotic in nature. Same goes with the increase in distance. As the distance increases and goes towards infinity, so will the force reduce to zero. So this is the nature of the curve when the force is proportional to the reciprocal of the square of the distance. Now, what does this tell us? Now, this force will obviously become will become zero at infinity. That means that this mass that we have over here, it definitely has it definitely has a field or influential blanket, so as to say, around itself, just like this, where this uh, blanket or this field in popular language uh, helps or causes the gravitational influence, and that is why this influential blanket is what we call as the gravitational field. Now, it's not restricted, of course. The blanket goes on and on. It goes on and on. But the effect of this blanket, or the effect of the field of this given mass, goes on decreasing like this. As the distance increases, the value of the force, attractive force, or even the gravitational field goes on decreasing in a similar fashion as inverse of the distance squared. Now, this gravitational field, however, must have some value at a given point. And how do we determine that? In order to do so, what we can do is we can just use a test mass over here. Let this be m0, this one that just I have just put a 0 under that mass, subscript 0, m0, that is taken as the test mass just to test the intensity of the field, of the gravitational field. And let us suppose that this is at a distance, say r, that we usually consider. So let us suppose it is at a certain distance r from the given mass capital M. So what we do is, in order to determine that, we first obtain the value of the force. Now the force is an attractive one. We are concerned with the magnitude at first. Obviously it is directed towards the mass because it's an attractive force every time, so the mass capital M will be attracting the mass small m0. Now the force here is given by gm m naught divided by r squared. This is the value of the force. Now, in order to determine the field, what we do is the intensity of the field, what we do is we just take that mass m0 or m naught and just vanish it from that point. And we do that just not just like that, we do that mathematically. Mathematics is handy in this case. We limit the mass m naught to almost negligible, that is 0, and then we divide that mass, we divide that force by that mass m naught. So what we end up with is the gravitational field intensity, which is along the direction of the applied force or the gravitational force. The intensity here is represented by the letter E. You can represent it by any letter, but here the gravitational field intensity has been represented by the letter E. Now, so E will be equal to, I put that limit over there, I haven't really applied it as yet, and then I just divide the mass m naught as mentioned in the above line, and I use the value of force, that is g m naught divided by r squared. Now the m naughts obviously get cancelled out. Now I can use that limiting value, I can just put it, it makes no difference now because the masses have cancelled out. So what I am left with is the gravitational field intensity, which is along the direction of r cap, that is directed towards this mass. So g m divided by r square r cap. Now this r cap obviously is directed towards the mass. Now this is the gravitational field intensity for the mass m that was present over there, and this intensity is found at a distance r from the given mass. Any other mass, let us say just small m, any other mass small m placed at a distance r from the mass m will experience a force which is equal to the force will be equal to the mass that has been placed, not this one, this one, the mass that has been placed, this one, from the given mass capital M multiplied with the intensity of that at that point. So what we end up with is the same thing that we had been discussing right from the very beginning. We have been discussing, that is m multiplied with a g m divided by r squared r cap, and this m just can come over to this side, and this is exactly the formula for the gravitational force on a mass m due to a mass capital M when they are separated by a distance r, and the direction, obviously r cap, as we have mentioned, is directed towards the given mass capital M. Don't get confused with the letters, the capital and the small letters. Just be careful about those things. That is why initially I have used m naught for the test mass, and that was just for testing, and that is why it has no role whatsoever with that intensity, with that magnitude or the expression of intensity that obviously vanishes, and we have done that mathematically. Now with the field intensity available to us, what we can determine is the field intensity in case of our very own Earth. Now any object which is placed above the Earth, it is at a distance equal to the radius of the Earth from the center. So this is the Earth, our very own Earth, and the distance from the center is the radius of the Earth, and any mass or any object at this point. Now because we have considered the Earth to be completely spherical, which is not the case, of course, it is an oblate spheroid or a geoid. It's the shape of an orange, but because we have considered it to be almost round in shape, the entire mass can be concentrated at the center. That is the rule of the center of mass of a system of particles. So the entire mass of the Earth can be considered to be concentrated at its center, and so any object which is lying at a distance r from the center will experience a gravitational force, and that force, the intensity of the force, can be measured by the gravitational intensity. So the gravitational field intensity at the point, we are just concerned about the magnitude as of now, that is equal to g, that is m divided by r squared. This is the mass or this is the gravitational field intensity of the Earth on its surface. Now for any mass m which is placed at that point, let us say over here, then that mass will experience a force which is equal to m times of E, that is mass times of the gravitational field intensity at the said point, and that is equal to g m times of g capital M divided by r squared. Capital M, remember, is the mass of Earth, and other masses are written in small letters. So what we get over here is simply m times of g m r squared. This is again can be rearranged in this form, which is the general expression, of course. But what's special about it? Well, we know that any object which is placed over the Earth's surface, it experiences a gravitational pull which results in its weight. So the weight of any object is simply due to the gravitational pull, which is of course the gravitational force that is being acted upon it by the Earth. And what is the gravitational force being acted upon by it? Well, if the object is of mass m, then the weight of the object is simply m times of g, g being the acceleration due to gravity. But hang on a second, what we will come up over here is that mg, the weight or the pull due to the Earth, is simply this one that we have just obtained in the above case. I'll use this expression for simplicity. m times of gm divided by r squared, and if you are comparing both of them, the m's can get cancelled out. So what we have is that the acceleration due to gravity is nothing but the gravitational field intensity of the earth on the surface. So that is what the acceleration due to gravity. And obviously acceleration, because one of the masses have cancelled out, this was the force devoid of the mass just has the acceleration in it. And so we have the expression for the acceleration due to gravity. We know its value, it is just 9.8 meters per second square. This was known, this was not known, we know it now. And now that we know the acceleration due to gravity, the expression for that, we can just use it to measure the mass of the earth. We determine the mass of the earth. Well, the mass of the earth in this case will be equal to g multiplied with r squared, r being the radius of the earth, which is 6400 kilometers nearly, and divided by the gravitational constant as already determined by Cavendish in his experiment. So this is the expression for the mass of the earth, and with the value of small g, capital G and r known, we have the mass of the earth as well. Approximately it comes out to be nearly 6 times of 10 to the power 24 kgs if you use those values that are available to us. And so it won't be really wrong to say that with this value of capital G, Cavendish actually literally weighed the earth. And therefore we can also determine the density of the earth, the density being equal to mass upon volume. So the density of the earth is simply the mass that we have over here. The expression for that is g r squared divided by capital G, and the volume is simply 4 by 3 pi times of r cube, that is the cube of the radius. We can just rearrange this, keeping the 4 pi below, 3 taken up and r cube staying down. R square gets cancelled with 2 of the r's, and what we are left with is 3g divided by 4g pi r, and use up all these values, it comes out to be nearly 5500 kg per meter cube. Obviously this is not a uniform case, this is the average density of the earth, the average density, because the earth has different mass distribution throughout its given volume. The mass distribution is not uniform. Only the above layer that we come up with has a density as low as 2700 kg per meter cube. So the inner layers must have a much higher density to achieve this kind of an average of 5500 kg per meter cube. Now, as we have understood about the acceleration due to gravity or the gravitational field intensity, this value may vary, variation of g. And how can we say that? Because this distance that we have taken here, the distance is right on the surface. Now spare a thought for those masses which are way above this earth's surface or within the earth's surface. So this value of g, as we can see from that expression over here, will vary with the height, that is altitude, or the depth in the inner surfaces, or in the inner region of the earth. So let's check how what that leads to, or so as to say how the variation occurs with the altitude and the depth. But before that, what we can also consider is the variation due to the shape. As I said, The Earth is not exactly this round shaped. It is somewhat of an orange shape, or more so as to say a geoid or an oblate spheroid. So this is what the shape of the Earth is. The rotation is quite fast, at a faster rate. We actually do not experience that, and thanks to gravity, of course, that the gravitational pull is so great that we hardly experience any kind of rotation of the Earth. Now, the rotation of the Earth causes this the flatness that occurs. This is more of a geoid or an oblate spheroid. This is what I learned in my school days. Oblate spheroid or geoid in shape. And the axis that we can have, well, these are not the axis, these are just the markings for the radius. Now this, let us assume, it's actually tilted. It's actually tilted by some angle, but for simplicity we will say that the poles are right at the top. So this is the radius of the pole, and this is the radius of the equator. As you can see, due to the flatness at the poles, the radius of the pole is obviously less than the radius of the equator. And using that, we can just compare the gravitational acceleration due to gravity, or the gravitational field at the poles and at the equator. So the gravitational field at the poles is simply g, the mass remains as such, divided by r p squared, while that for the equator is gm divided by r e squared. Now take the ratio. What you can find is that gp divided by ge, that will end up with a ratio of re by rp squared, because they are in the inverse form. So the other one goes up while the first one goes down. And as we know that re is simply greater than rp, so this thing will be greater than 1. And then therefore we can say that the gravitational force at the poles, or the gravitational pull at the poles, is greater as compared to the gravitational pull at the equator. Or as we descend from the poles towards the equator, the gravitational influence, or the acceleration due to gravity goes on decreasing from pole to the equator, just like this. With the shape of the Earth, the gravitational pull goes on decreasing as we move from the poles towards the equator. And at what rate does it decrease? Well, we can just take the subtract them with the radii available to us, the distance from the center of the Earth. What we have determined is that the change in gravitational pull, or the change in the acceleration due to the gravity, that is from the poles towards the equator, that nearly results in approximately a change of 0.018 meters per second squared, approximately 1.8 centimeters per second square, so as to say, not a drastic one, but still it can be taken into account. Now, if we consider the altitude, the case of the variation of g with respect to the altitude, we can go back to the round shape of the Earth for simplicity, because we are considering a point away from it. So this is more or less the round shape of the Earth, and this is the center. From the center we have a radius r, and from that let us assume a height h above the surface. Now at that height h, the gravitational force, or the gravitational field intensity, let it be g dash or g primed, and that will be equal to g m divided by r plus h whole square. But on the surface over here, what we get is simply g, which is equal to gm divided by r squared. Now if we take the ratio of both of them, what we find is g dash divided by g will be equal to well, once again we have r plus h at the denominator and r square at the top, because it is inversely proportional. You can just write that explicitly and then cancel out those gm's, and you will find this same result. And then what we do is we just take the r square from the top, or divide the top and the bottom with r square. Now r square divided by r square goes to 1, and r square divided over here is simply r plus h whole squared divided by r. This can be taken entirely within the bracket. Then the r and the r over there at the denominator cancel out to give 1, and finally we have h by r whole squared. Now this value that we have over here, from this value what we have is 1 plus h by r. Now this can be written in this form, of course, because as it goes up, the power becomes negative. Now because of this h, if at all it is much less than r, so this term that we have over here can be expanded, and expanded binomially. With the binomial expansion, we have the minus 2 coming down and getting multiplied with h by r, and the rest of the terms, the higher order terms, can be neglected. So what we end up with is that, because why neglected? Because that will be in higher powers of h, and obviously h is much less than r, so they obviously have to be neglected. Now this is 2h by r. So this is the ratio of the gravitational fields and of the new field with respect to the old one. And just to give you a comparison, this is this much. Now this was on the surface, this is at a height h. So as we can see from this negative sign that we have over here, the gravitational pull or the field due to gravity decreases, which is quite okay, because with the increase in distance the field must decrease, is what we have learnt so far, and this is exactly giving us the evidence of what we have learnt till now. But let us consider the case where the object or the field is to be obtained at a certain depth from the surface. Now this was the surface, and it is at a distance r, of course, but now we consider a point over, let us say here, r is this complete distance, that is the radius, but this distance that we have over here is less than r. So what we expect is the force or the acceleration due to gravity to be higher, because with the decrease in distance the gravitational pull will increase, is what we have learned. So let's check that. Now this distance is at a depth d. The depth d, if you are unable to see it, let me just mark it. So this is the depth d from the surface, right? And because we have excluded this upper region, we can just construct a dotted circle which will separate the masses that are lying underneath that depth or within that radius. What we are trying to say is that I am shading a portion, and this mass will be responsible for the gravitational pull at that point, not the outside mass. The outside mass with the value of d much less than that of r the outside mass won't really count, because that will be a very thin layer as compared to this layer. Now again, I'm giving you an idea that if we are considering that this given um, this piece of earth that we are considering, the density, as we had discussed earlier, the density was high in the inner parts, while the density was as low as 2700 in the outside part, and the average came up to be 5500. So obviously the more mass concentration in the inner parts than the outside. So the outside thinner layer that has been considered will contribute a lesser amount in the gravitational pull, with the consideration that D is much less than R in this case. This is pure mathematics, what I'm talking about right now. Uh, as I discuss the topic further, you will be able to understand if you haven't. Now, so for the inner shaded portion that we have over here, that let us assume that it has a mass m dash. We will just get to it, get to the mass very soon. Now 4 by 3 pi r cube is the volume of the earth, and that, if the mass distribution was uniform, then that has a mass m. So a unit volume will have a mass m divided by 4 by 3 pi r cube, which is obviously the density. Now this volume that we are considering now is having a distance, let us say r minus h, as you can see, r minus d, exactly, not r minus h. So this volume is for the radius r minus d. This is that radius, and this is simply r minus d, because d was this region over here. So 4 by 3 pi, now the new radius for that new region, shaded region, is r minus d whole cube. So now as we take the, or consider the mass over there, that is m dash, is simply equal to m divided by 4 by 3 pi r cube, that is the total mass divided by the total volume, multiplied with the given volume, that is 4 by 3 pi r minus d whole cube. Let me take the whole cube over here for convenience, for making it easier to write. So what we have with us right now is r minus d, and this r can be taken inside whole cubed. Seems all right as of now. But the acceleration due to gravity now will be g dash, and this is the g dash at the depth d. So this is g dash is equal to g times of m dash divided by the distance, obviously now is r minus d whole squared, and that leads us to g m dash. Instead of m dash, we have this entire thing over here, that's m r minus d whole cube, r cube, and at the denominator over here, r minus d whole squared. This entire thing can cancel out, and we are just left with r minus d. Now this can be rewritten as gm divided by r square. I keep the r square from that r cube at the denominator, and one of the r is left. What I do is r minus d divided by r, I take it to that side, or below that parenthesis, and then what we have is this gm by r square is simply small g, that is the acceleration due to gravity on the surface, and this r minus d divided by r, well, r by r is 1, and this is 1 minus d by r. This is the new acceleration due to gravity at a depth d, and as you can see, the expressions are quite similar. With that negative sign, again we are obtaining a decrease in the value of the acceleration due to gravity, as opposed to the proposed increase. Why? Because the masses have been left out. A small amount of mass is acting Again, the small amount is not that small, but it's definitely less than the total mass of the Earth. And so there is a decrease in the gravitational force or the gravitational acceleration. Now remember, the thin layer of mass that is outside, that will be attracting any object which is placed at that depth d, that will be attracting the object towards itself. And this heavier mass, which is the inner mass, the shaded portion m dash, that will be attracting the mass towards itself. So resultant pull due to this shaded mass, that will obviously be less, because the outside mass will be attracting that as well. We have left that attraction as of now, considering that the outer mass is negligible as compared to the m dash, which is the inner mass, but nevertheless it is less than the total mass m of the Earth. So this is just a comparison of how the gravitational pull or the gravitational field intensity changes with the altitude or with the shape. Now, from all the cases that we have seen, with the altitude as well as with the depth, the gravitational force goes on decreasing. It will obviously go to a value 0, as we have this formula. This goes on decreasing with the negative sign. It will go on to 0 if d by r is simply 1, because 1 minus 1 at that point of time will be 0. So g dash will be, or will tend to be 0 when d by r is equal to 1, or we have d going to be nearly equal to r, means the depth. Exactly, if you dig into the center, you probably won't experience any gravitational pull whatsoever. The gravitational field at that point will be 0. So a hypothetical case that we can consider from this is that, what if one digs a tunnel? What if one digs a tunnel? This is a hypothetical experiment, of course, a thought experiment. What if one digs a tunnel right through the Earth from one end to the other end? Now what happens over there? Now you drop an object from the surface and it goes in. Now as it goes in, the acceleration due to gravity goes on decreasing, following this expression that we just obtained over here, and it goes to 0. There's no acceleration at this point, at the center, as it reaches this point. But obviously it was experiencing some acceleration, and as a result of that it has experienced a certain force, and that will just cause it to overtake or cross this region and go near about this point on the other side of the surface. And then again, because there was a hole over there, and it returns back. Let me give it to you in another ink for better understanding. So what essentially we did over here is that we dug out through the Earth, and we allowed an object to fall through. This object falls through to the center. It is propelled by the force that was acting on it. Even though the force at the center is 0, it was propelled further till the surface on the other side, and then it was dragged back in. And again, as it is dragged back in, it is propelled further to the other surface, and likewise it goes on oscillating in simple harmonic motion. But that is not to be the case, because the Earth is rotating, so that will be a damped oscillation. This is a hypothetical or the thought experiment that many have carried out, but not it won't fusion, because of the kind of motion that Earth exhibits and the kind of structure that Earth has, the core and the mantle and everything. If you are a geology student, you would probably understand about what I'm talking. You probably had all of this in geography in your school. Speaking of geography, you must have come across the term latitude. And what does it mean? Well, these are just imaginary lines which are horizontal lines. Of course, the longitude are obviously the vertical lines encompassing various regions on the earth. Here again we are considering the round shape of the earth. With respect to the latitude also, the gravitational influence is changing or changes, as we have discussed the case of poles and the equators. The We have conformity for that in terms of equations that we are about to obtain over here as well. So of course the poles are tilted, but here we will be taking them as vertical as possible, and this one is the equator, the equatorial line right through the center. We consider latitude at this point, and supposedly it has a radius, say it is equal to r. Any object that is placed at this point, that object will obviously be experiencing a direct force towards the center due to this Earth's pull, and the mass of the object being m, it will be experiencing a force of say mg, which is its actual weight. Now if, and this was the case if the Earth is not rotating. Now as we know, the Earth obviously rotates, and this fellow over here, it will be moving along this circular path that is along that latitude, right? And it will be experiencing a centripetal force, and a centrifugal force will be acting along this direction as well. Now the centrifugal force that will be acting, that will be acting away from the center. And what is the value of the centrifugal force? Now let us say that this is making an angle theta with respect to that the center and the point on the latitude. At that point P, let us say it is making an angle theta. And as a result of that, what we have is that this radius r that we are having, this small r of that latitude, that will be now this complete radius of the Earth, as you know, has been taken as capital R right from the very beginning. So r is simply equal to r cos theta from the geometry of it. And then we have the centrifugal force. Centrifugal force here is, let us say, Fc is the centripetal force, Fc dash is the centrifugal force, and that is equal to mr omega squared, omega being the angular speed with which the Earth rotates about its axis. Again, that axis, as I say, has been taken vertical, but as you know, it is tilted. So the poles lie over here, and the equatorial region that lies along this line. Now with all of this available, what we have is just to determine the apparent weight that a body experiences or is measured when we consider the case of rotation of the Earth. Because of the rotation, this centrifugal force that we are viewing over here, that centrifugal force will cause the effect of this gravitational force to lessen. And the let me draw this complete thing that I have encircled right now at a different place for a clear view. This is the center. So from that point P over to the center is how the weight acts, and this is equal to mg. And then we have the centrifugal force, which is acting along this line, that is Fc dash. And from the parallelogram law, of course, we will have the resultant of these two forces is where the apparent weight of the object, and that is what we exactly measure, the apparent weight that that we come across day-to-day life. And that is obviously because of the rotation. The centrifugal force results in such a kind of a behavior, but we will see how that affects us in various regions. Now this being theta, this being equal to 90 degrees, of course, this complete thing that you can have is simply 180 minus theta, because if this is theta, this need not be 90, of course. uh, this will be equal to theta, and this entire thing being 180, this is 180 minus theta. That's what the geometry says. And so with that resultant that we have, we can have the value of mg dash. Now mg dash will simply be equal to the resultant of these two, that is mg, which is the actual weight of the object, plus mr omega squared, which is the centrifugal force whole squared once again, plus 2 times of mg times of mg omega squared cos of 180 minus theta. Now cos of 180 minus theta is obviously minus cos theta. So what we end up with is that the m's can get cancelled out on either side, because they will be in squared. On the right hand side, taken under root, it will be simply m. So the m square taken under root, and then coming out of it, that cancels out with this m over here, and what we are left with is simply g dash, and that will be equal to, well, if you observe closely, what we have is the g can be taken common, and so the first term goes to 1. The second term has well, instead of that small r over here, what we have is this value r cos theta, and we can take it like that as well, r square cos square theta divided by g, and omega to the power 4 in that case. And finally this will be in minus, because this is minus cos theta. Cos 180 minus theta is simply minus cos theta, so the minus can be taken into account, and we have 2r omega squared cos squared theta. In case you are wondering where this r square came up with, well, that was because of the uh, this value, that is r, small r is equal to capital R cos theta, and there was a cos theta outside as well. So now we have that divided by g, which was taken common, and all of this under root, so to the power 1 by 2. Now this term that we have, this fourth power of omega, that's much smaller. So when compared to these two terms, this term can be neglected, and what we get is that we have the value of g dash to be equal to g times of 1 minus 2r omega squared cos squared theta divided by g, and that too taken under root. Now r omega squared is much less than g, so what we get is simply the binomial expansion of it, that is 1 minus half times of 2r omega squared cos squared theta divided by g, and this, the 2's get cancelled out. We have g dash to be equal to g minus r omega squared cos squared theta. The g gets multiplied inside and cancels out with the g in the denominator as well. This factor, this entire thing that we have over here, that tells us that how it varies. Now obviously at the equator, what you have is theta to be equal to 0 degrees at the equator, and at the equator, theta being equal to 0, you have the maximum possible value. So g dash at the equator is simply g minus r omega squared, which is the least value of acceleration that is experienced. And as we know that it varied by a certain amount, let us see what it does in the poles. At the poles, theta is simply equal to 90 degrees, and with that value going to 90, cos 90 is 0, so g dash is equal to g. Here your apparent and actual weights will be the same, and so with that value available, what we can have over here is r omega squared. And as you know, We have just determined the difference in the acceleration due to gravity between the poles and the equator, and it was somewhat 1.8 centimeters per second squared, which is the value that we obtained over there for r omega squared, neglecting the higher terms, of course, as in this case we have done for the higher power of omega as well as cosine. So that's the variation of the acceleration due to gravity with at the poles and the equator and at different latitudes. And well, what we come up from this is that the acceleration due to gravity will be least at the equator, also because of the fact that if you tend to multiply this with the mass, just multiply this with the mass. Now this was the apparent weight. If you are multiplying the mass on the left hand side, you multiply it on the right hand side as well. So this is the actual weight without the rotation, and this, if you observe it closely, this is the value of the centrifugal force, which is the maximum at the equator owing to the radius, complete radius r of the earth. So in that case, you have the factor of the weight going down by the centrifugal force, the maximum centrifugal force due to the maximum distance from the center of the earth. So this is how the variation of the centrifugal or the variation of the weight of the object and the gravitational field works for different places and different and the difference in the shape of the planets in particular our very own Earth. And in the next video we'll be discussing about the potential energy that I had mentioned in the previous video. We couldn't do that in this one, but definitely we'll be doing that in the next upcoming video, and we'll be considering various cases as well as the proof of the Kepler's law to be followed in the upcoming videos as well. But till then, thank you for watching.